Sometimes we're looking for a probability, not even a conditional probability, just a regular probability. And it turns out that introducing conditional probabilities into the problem can make our probability easier to find. So in particular, sometimes we want, say, probability of A, but probability of A given B and probability of A given not B are easier to find. Or maybe we want probability of A given E, which is conditional, but probability of A given B and E, or probability of A given not B and E, are easier to find. So then we can write, in the first case, probability of A equals probability of B and A plus probability of not B and A. Which is probability of B times probability of A given B plus probability of not B times probability of A given not B. Or in the conditional case, if we want probability of A given E, or we write probability of A given E equals probability of BA given E plus probability of not BA given E. And then this equation becomes probability of B given E, probability A given B and E, plus probability of not B given E times probability of A given not B and E. So writing either of these equations that introduces the conditional probabilities is called conditioning on B. Alright, so let's do an example, and maybe I'll copy the formulas down here so I can have lots of space to do the example. So we have probability of A equals probability of BA plus probability of not B and A, which is probability of B, probability of A given B, plus probability of not B, probability of A given not B. So it's this equation, and then probability of A given E is probability of B and A given E plus probability of not B and A given E, which is probability of B given E, probability of A given B and E, plus probability of not B given E, probability of A given not B and E. Oops, went off the screen. There we go. Alright, so now for example, this is an example from the book about an insurance company. So an insurance company classifies drivers as good or bad. It believes that 70% of the population, 70% of the drivers are good and then 30% are bad. And it believes that in any given year, a good driver has an accident with probability 0.2, and a bad driver with probability 0.4. So let's define some events here. So let's let AI be the event that a driver has an accident in year I. I guess technically one or more accidents in year I, and let's let G be the event that the driver is good. So the question is, what is the probability that a driver has an accident in the first year that they get their policy? So this would be easier if we knew whether the driver was good or bad. So we can condition on whether the driver is good or bad, and write probability of accident in the first year is probability of having a good driver have an accident in a good year, plus probability of having a bad driver and having that driver have an accident in the first year. So this is probability of, using the multiplication rule, probability of G, probability of A1 given G, plus probability of not G times probability of A1 given not G. So we said what fraction of people are good drivers? 0.7. Probability of having an accident being a good driver is 0.2. Probability of being a bad driver is 0.3, and then the probability of having an accident, given that somebody is a bad driver, is 0.4. So we got 0.14 plus 0.12 equals 0.26 is that probability. Alright, now let me write this somewhere and then do another problem involving the same insurance company. Alright, to make room, let me summarize all this with just a couple of equations. So we have probability of a good driver equals 0.7. Probability of, well, I'll define the events. G means driver is good. I means driver has accident in year I, and we're given that probability of good driver is 0.7, probability of having an accident being a good driver is 0.2, and probability of having an accident in any year being a bad driver is 0.4. And we just computed that probability of having an accident in any year, say the first year, is 0.26. Now, implicit in these probabilities is the assumption that AI and AJ are conditionally independent given G. Because when we say that the probability of having an accident in year I given G is 0.2, there's no dependence here on whether the driver had an accident in year I minus 1 or I minus 2 or I minus 3. So apparently no amount of accidents or accident-free years changes the insurance company's mind once they classify somebody as good or bad. Well, I think that's a pretty strange assumption. Definitely unrealistic. Seems to me that as soon as somebody has an accident, the insurance company changes their opinion of what kind of driver they are. And the premiums go up if you have an accident. And they have specials, like if you go so many years with no accident, then your premiums go down. So I think the insurance company is collecting information as the years go on, and they are changing their opinion depending on accidents of the driver and accident-free years for the driver. So this is unrealistic because insurance companies do update opinions based on accidents or accident-free years. I'll have more to say about this later meaning in another lesson. Okay, so to write down, I better write this more briefly because it's taking up the whole board. Let's see, so I guess I'm saying that probability of AI given G and AJ is just probability of AI given G. So no information about accidents in another year is going to change this insurance company's about the probability of the driver having an accident in a given year. Knowing that the driver is either a good driver or a bad driver. All right, get rid of my rant here. And make room for the question and its solution. the question is, what is the probability of having an accident in the second year given that there was an accident in the first year? To solve this, we'll condition on G. So the probability of an accident in the second year given an accident in the first year is the probability of G and having a good driver and accident in the second year given an accident in the first year plus the probability of not G and having an accident in the second year given an accident in the first year. All right, now we can take these expressions and use the multiplication law, the multiplication rule, the version for conditional probabilities, to break these up as probability of G given A1 times probability of A2 given G and A1 plus probability of G bar given A1 times probability of A2 given G bar and A1. Now we said that probability of AI given G and AJ is just probability of AI given G, which is maybe unrealistic, but that's what's given to us in the problem. So that means that this is just probability of A2 given G, and this probability here is just probability of A2 given not G. So now we need to figure out what probability of G given A was, because that is not one of the probabilities that we're given. We're given things of the form probability of A given G. So this is an opportunity for us to use Bayes' law, which helps us turn these around and use the data that we have. So probability of G given A1 is probability of G and A1 over probability of A1, which we computed in the other problem, which is 0.26. And then probability of G and A1 is probability of G, probability of A1 given G, and that's something that we know. So this is probability of G is 0.7, probability of A1 given G is 0.2 over 0.26, and then this probability, let's see, I'll draw an arrow for this because we know a number for this. Probability of A2 given G is the same as probability of A1 given G, because the year doesn't matter. So that is 0.2. And then here we have, I guess we'll have to use Bayes' law again. Well, actually, probability of not G given A1 is 1 minus probability of G given A1. So 1 minus this fraction here. So 1 minus 0.7 times 0.2 over 0.26. Times probability of A2 given not G. So the probability of an accident given a bad driver is 0.4. And then we can type all of this into the calculator or reduce fractions, and I get that it is equal to 19 over 65. So the main point of doing this problem today is just to practice conditioning and double conditioning, when you already have a conditional probability and then you're conditioning on some other event on top of that. And maybe a secondary point is the comment that I put about the problem being unrealistic. Because this is the type of situation where the more you observe, the more of an opinion you form. These aren't independent trials of flipping a coin where no matter how many times you flip the coin, you've inspected the symmetry and you still say probability of 1/2 for heads, probability of 1/2 for tails. The end.